Okay, so here's our kinetics crash course. The first thing we have to know are reaction rates and factors that can affect them. So all of these factors that are listed here, concentration, temperature, surface area, and even adding a catalyst. Anytime those are increased, concentration, temperature, and surface area, then what it does is it increases my rate as well. If I add a catalyst increases my rate as well. So all of these factors here increase the reaction rate. Now, one thing we have to be able to do is argue why that is the case. So anytime you have to justify why any of these increase rate, we need to talk about effective collisions. In order to have an effective collision, two things have to be met. The first is proper orientation, which means that these molecules are basically hitting in an exact spot to where it can break the bonds. And the second thing is sufficient energy to overcome activation energy. We talked about activation energy in the thermo unit crash course. So that's like the hill you have to get up to be able to get your reactants to go to your products, and it can go in the reverse direction as well. Activation energy must be overcome in order to break the bonds for the reactants and make your products. So these are the two things that you need to talk about whenever you're justifying. So I increase the likelihood of effective collisions because I increase proper orientation and increase the likelihood of having sufficient energy to overcome the activation energy. Catalyzed versus uncatalyzed reaction. So again, a catalyst lowers activation energy, and it does this by providing an alternate pathway. There are different types of catalysts. There's homogeneous catalysts and heterogeneous catalysts. A homogeneous catalyst is where the catalyst and the substance that the catalyst is in are the same state of matter. So a liquid catalyst is in a liquid substance. A heterogeneous catalyst is when the state of matter of the catalyst is different from the substance that it's going in. So for instance, a solid catalyst going into a liquid substance would be a heterogeneous catalyst. We have catalysts naturally in our biological systems. Those are known as enzymes. So when I look at my potential energy versus reaction coordinate graph, you have to be able to draw the catalyzed versus the uncatalyzed reaction. So the red right here is representing the uncatalyzed reaction, and the blue is representing the catalyzed reaction. What this catalyzed reaction does is lowers the activation energy because it's basically providing an alternate pathway for that reaction to take. It's kind of like a shortcut for the reaction. One thing you've got to pay attention to, you see how my reactant's energy and my product's energy does not change. So it's not changing my delta H of the reaction, it's not changing delta G. The only thing that a catalyst does is lower the activation energy. Now let's talk about the different types of rates. So first we have the smaller questions that they don't really ask a lot about, but we still need to know. The instantaneous rate versus a relative rate. Instantaneous rate is the rate at an instant of time. So it's the rate at an instant of time. And so I have here a concentration versus time curve. And you see how it's a curve. So what if I wanted to know the rate at that particular time right here? Well, what I would do is I would draw a line tangent to that curve. So a line tangent to the curve. And from that line tangent to the curve, I can find my slope, which is rise over run. So I find my slope. And that slope is my instantaneous rate. For relative rates, this has to do with stoichiometry. When I have the rate of something, let's say O2, and I want to find the rate of N2O5, I have to set up a proportion basically. And the proportion is all about your your stoichiometric coefficients. So if I have the rate of O2, it has a coefficient of 1, and I set it equal to the rate of N2O5, which has a coefficient of 2. So now if I have this rate and I'm trying to find this rate, I just use my proportion and cross multiply. So anytime you have the rate of something in a reaction and you want to find the rate of something else in a reaction, you set up this proportion. That is relative rates. Now let's talk about the rate law expression. So rate law expression, remember, does not include any numbers. So rate equals K. K is your rate constant, so I'm going to put that down here, times the concentration of one substance raised to its order, the concentration of the other substance raised to its order, and you can keep on going. Remember that you do not include any numbers if you write a rate law expression except for the orders. Our orders, if you remember, are 0, 1, and 2. If I have something that is 0 order, then that means that the rate is not affected by your change in concentration. So my concentration will change, but my rate does not change. It stays the same. If I have something that is first order, whatever the change in concentration is going to be the same proportion of my rate. So for instance, if my concentration doubles, then my rate is going to double as well. If my concentration were to triple, then my rate would triple as well. Second order is basically the exponent of 2. So my concentration change will cause my rate to change by the second power. So here's an example. If I have a change in concentration of 3, my rate is going to change by 3 squared, which is 9. If I had a concentration change of 4, then my rate would change by 4 squared, which is 16. So this is where that second order comes in, the first order comes in, and 0 is not affected at all. So you can treat it like it's some number raised to the 0 power, which is just 1. So we put these orders as exponents, and that is showing the relationship between your concentration change and your rate. The next thing we have to be able to do is work with our rate constant. Our rate constant is temperature dependent, so the only time that it changes is when temperature changes as well. Don't forget, the units for K are tricky and they always change. So the units for K are 1 over molarity raised to the overall order minus 1 times the time value. So for instance, if I had this particular thing, A was order of 2 and B was an order of 3, my overall order would be 5, so my units would be 1 over m 5 minus 1, which is 4, times whatever time unit you're working with. Don't forget to do these units because you always get 1 point in addition to finding the correct value of K. Now let's look at differential law. When you do differential rate law, this is where you have your table logic. If I am trying to find the order of NO, I have to make sure that Cl2 is kept constant. Then I look and see what is happening to my rate and my concentration. So if my concentration doubles and my rate doubles as well, then that means that NO would be first order. If my concentration were to double and my rate were to quadruple, then that would mean that the NO is second order, and so on and therefore. If I want to know the order of Cl2, then I have to make sure that NO is held constant. And then I do the same table logic there according to the order. Once I know the order, I can write my rate law. So rate equals K, and then I would put in NO. Let's just say, for the sake, it's first order. And let's say Cl2 is second order. So this would be my rate law expression. If I wanted to find my rate constant, K, then all I would do is find one of these experiments and plug in this information into my rate law expression and solve for K. Once I find the value of K, I then find its units, which is 1 over molarity, overall order minus 1, which is 2 plus 1 is 3, minus 1, 3 minus 1 is 2, and then times the time unit. To find your time unit, you always look inside your table. So this table has seconds, so that is my time unit there. So this is always a 2-pointer for your K value. You get 1 point for the value, and you get 1 point for your units. If I had a first order reaction, this particular line would be straight with the natural log of A versus time, but this curve and this would curve as well. So that's how I determine which order is. It's out of the 3 graphs, whichever is the straightest line. That is the order of the reaction. To find K for integrated rate law, I take the absolute value of my slope. It's always absolute value because these are negative slopes for first and 0 order, and the second order is a positive slope. So the absolute value of my slope is K, and I find the units the same way, alright? Units the same way. So it would be the overall order minus 1 times the time unit, and that is all underneath 1. The next thing we have to be able to do is half-life. So half-life is defined as the time for half of the concentration to disappear. So you can use your concentration versus time graph and say, all right, well, my initial concentration was here. Half of that substance is going to be right here. So however long it took to have half of my substance remaining is the half-life. My second half-life would be 400 times 2, which is 800 seconds. And then my third half-life would be 400 times 3, which is 1200 seconds. So you can be able to interpret and analyze this graph with the half-lives. Another type of question that they like to ask with this is if, for instance, you know that your half-life is 10 seconds and you start out with 100% of that substance, what percentage would be left over after 30 seconds? So the way you work this out is you say, all right, well, 30 seconds is 3 half-lives because 10 and 10 and 10 is equal to 30 seconds. So if I have 100%, it's going to have 1 half-life. The arrows represent half-life. 1 half-life is going to have 50% remaining. A second half-life is going to have 25% remaining. And then a third half-life is going to have 12.5% remaining. So that would be my answer. So they like to work backwards from this. They like to start with grams. So it's very important to know how to do that. It's very easy points. The last thing you have to know how to do for half-life is an actual equation. So half-life is equal to 0.693 divided by K. This is your rate constant. This is for first order reactions only, right? So it's only for first order reactions. There are half-life equations for 0 order and second order, but we don't do it in AP Chem. One thing that is tricky about this is knowing that this half-life for first order is not concentration dependent. It only changes when your K value changes. And since K is temperature dependent, it only changes when you have a temperature change. Sorry about that. Okay, so where was I at? Okay, we were talking about elementary steps and whether or not we have an intermediate or a catalyst. So we have to be able to cross those out first. An intermediate begins as a product and then is broken down again as a reactant. A catalyst, however, would start at the beginning of the reaction and it would come back at the end of the reaction. We still mark out catalysts, but you do have to be able to distinguish the difference between the two. So an intermediate starts out as a product, a catalyst starts out as a reactant, and they're always crossed out somewhere in that reaction. So with this, there's a couple of things you have to do with reaction mechanisms. First of all, you have to determine the rate determining step. The rate determining step is the slow step that is in this process. So let's say that we have an experimentally determined rate law. That is found from either integrated rate law or differential rate law. That's what experimentally determined rate law is. And that rate law was rate equals K NO to the second order. In order to figure out what my rate determining step is, I have to match this experimentally determined rate law with the rate law from the mechanism. So I would write the rate law for each step. So rate equals K NO to the second order first. And this one on the bottom is rate equals K O2. And I continue to add up the elementary step rate laws until I reached my experimentally determined rate law. So you see how if I stop at this first step, then that is equal or equivalent to that rate law that I found experimentally. So that means that this first step, the elementary step, is my slow step, which is my rate determining step. If my rate law experimentally was rate equals K NO to the second O2, then my second step would be my slow step because I would just combine the first and the second step rate laws to find my overall. When you are justifying your slow step in the reaction mechanism, you want to clearly term that the reason why this step is the slow step is because the rate determining step, rate law, is equal to the experimentally determined rate law. They're very exact with the wording of that. The last thing we need to talk about is activation energy. In order to be able to find activation energy and actually calculate its value, you have to do experimentation with this as well. So you have natural log of K. This is your little rate constant that is on your y-axis and 1 over temperature on your x-axis. When you do that, you get a straight line that is a negative slope. This slope is equal to your activation energy as well as your gas constant. So it has gas constant and activation inside there. So it looks like this. Slope is equal to, it's a negative slope, activation energy over R. Now, this R is your 8.31 R because it's dealing with joules. with energy. So if I have this slope, then I can solve for activation energy, which is negative R times slope. So that is how I would calculate activation energy.